You just have to notice that in this case f is nilpotent if and only if, as we would have described, f bar equals 0 in the quotient I. Of x for any I prime of A. Well, this is always obvious. You only have to show this. If f is nilpotent, f equals 0, f bar then equals 0 in this A quotient I, but this is integral domain. This is integral domain. It implies equals 0, right? This is it. So let's do the next one. F is a 0 divisor. If and only if there exists a non-zero constant just in the coefficient ring such that f equals 0. Because by definition this is equivalent to there exists some g, fg equals 0, non-zero polynomial. But now you only have to show that there exists some zero constant. Again, let's just apply by computations. Still, suppose our f is a 0 a1x until an x to the power n. Suppose this g is again b0, b1x to the power m. And then what do we have? Let's again look at the highest degree. We have a bm equals 0. Look at the plus m minus 1 degree. We have this, and correspondingly similar you got what we want. And this tells you that we only need to find element in the coefficient ring which kills f, which means kills all the coefficients of f. But here we find bm kills an, but we don't know bm kills an minus 1 or not, but bm squared kills it. If we times by bm on both sides of this equality, you will see that bm squared kills an minus 1 because bm kills an. And similarly, we will say that bm to the power, just make it bigger enough, kills all the ai. Okay, you can make this precise issue. The smallest one should be, so this is bm to the power 1 corresponding to n, 2 corresponding to n minus 1. So if you want to kill 0, you just put n plus 1. You know what I'm saying? n plus 1 kills b0. Okay, and so this bm to the power n plus 1 will kill f. And the other direction is obviously true. The last one f is primitive, by definition, if all the coefficients generate coefficient ring as ideal, that is to prove that times G is primitive, and finally if F and G are both primitive. So this one is not very obvious, but let's just do the computation at the beginning, just describe it. So suppose you have your F again is 0, you want x to the power n, and you got your G b0, b1x, bm to the power m. So primitive, let's first show this direction. If f is primitive, g is primitive, I want to show f and g are correspondingly primitive. What do? We first, so the question is about 3 ideal. The first ideal is the one generated by, let's call this I1. The second one is about this generated by coefficient of g, and the second is the one generated by the coefficient f times g. We know what should be that. Degree 0 term is a0b0, then degree 1 is a0b1 plus a1b0. Similarly, finally an bm. Okay, let's call this I3. So the question is I1 equals 1, I2 equals 1. Is it equivalent to I3 equals 1? So firstly, let's observe that I3 is contained in I1, because each element is every element generated by this, every element in this idea is generated by A0 to A, and similarly it's also in I2. This tells that I1 equals I2 equals this tells that if I3 is already the identity, then so is I1 and I2. What is left to prove is that I3 equals I1 and I2 are identity, implies I3. Right. How do we do that? Proof of this would be, suppose this is not the it's not the identity ideals. There is some maximal ideal containing this I3, right? And then I want to show that there is some contradiction, obviously. We got this maximal ideal. What we want to do is look at its quotient. This gives us a field. this gives us also a map this f to f bar. Knowing that I1 and I2 are both identity, which means that let's recall the definition. Right, this is one. In particular, this is not 0, because if this is 0, this will tell you that all the coefficients are in maximum ideal M, and so will be the ideal generated by it. So this is not the case. Otherwise it's containing M, okay? It's not containing M. Similarly, this is not 0. But then you're claiming that this is 0 because what? Because all the coefficients, recall that this is just all the coefficients of fg. All the coefficients are contained in M, so this is 0. This gives you contradiction. And so we finish the proof.